Next problem is also again on the laws of motion, right? And in particular, basically looking at forces on a particular system. Let's get started. A 10,000 kilogram locomotive pulls a 20,000 kilogram train car down a level track. Draw a free body diagram of the system. If the acceleration of the train is 0.1 meters per second squared, this should be A. Draw the free body. B. Find the new force the net force acting on the locomotive train car system. C. The net force acting on the locomotive. D. The net force acting on the train car. So let's draw a little diagram of how this thing works. All right, so let's draw the locomotive first. So locomotive is going to pull a train down the level track. So let's draw a locomotive, all right, as old-timey steam locomotive. So this is why I'm a physicist and not an artist. Okay, but you get the drift. Okay, so this is my locomotive. And I'm going to drag along a train. Okay, along a level track. Right? Now, the mass of this locomotive is 10,000 kilograms. And the mass of this train car is 20,000 kilograms. Right? It's a little something big and fairly heavy. Okay, so let's draw a free body diagram of this system. Right? Well, if you were to draw it for any particular one, right? Basically, you have if you you have to basically pick each particular system and draw the free body diagram for that. Right. So for part A, okay, let's do the locomotive first. Right. So that's the locomotive. Right. As a point, okay, there's going to be a force that's going to be exerted on it. This is the force that will accelerate this train. And then there's basically another force, which is happening from this linkage here, right? This is the force of the train car on locomotive. Okay, so, right. Let's label this as 1, this is 2. And so that makes it a little easier. And if we're trying to write a train car on locomotive, we'll write just the force on 1 by 2. Okay? And then the net force acting on this particular system. Okay? Now, for the train car, this is number 1. The same thing. This is 2. There's only one force acting on this, basically due to the linkage between the locomotive and the train. So there's going to be some force here, which is the force of on 2 acted on by 1. Right? So this is force on the train car by the locomotive. Right? Now, Newton's third law says for every action there's equal opposite reaction, which really means for every force there's equal opposite counterforce, right? And so what that means is that if I exert a force on the train car by the on the locomotive by the train car, that's equal to the force, the opposite the force on the train car exerted by the locomotive. Okay. All right. So that's basically the free body diagram of the system. All right. Okay. Now let's find the net force acting on the train car locomotive system, which is this force right here. Okay, the net force. All right. Okay, so the net force, the net force is equal to the mass times acceleration. We can drop the arrows right now because we're just looking in just one direction along the x-axis, but we'll just keep it. So let's say that's the x-axis. So the force is going to be some force, which I don't know, is equal to the mass, which is the mass of two systems, which is going to be basically the mass of 1, which is a locomotive, plus the mass of 2, which is a train car, times the acceleration, right? And the acceleration, okay? And the acceleration I know is going to be 0.1 meters per second, A, 0.1 meters per second squared along the positive x direction. So this is equal to, so m1 is going to be equal to 10,000. m2 is going to be equal to 20,000. This is kilograms times basically 0.1 meters per second squared is equal to, so this is 30,000 times 0.1 is 3,000 newtons. Kilograms meters per second squared is newtons. Alright, so boom, we got the net force acting on this train car locomotive is 3,000 newtons along the positive x hat direction. Okay, now let's look at C. Okay, the net force acting on the locomotive. Now there are two ways of basically solving this problem. Okay, the first way is to note that if there is the net force always causes acceleration, which is always to use like F equals ma, right? In which case it becomes very easy now. You just have to write down what the acceleration is, and then instantly you know what the net force needs to be, just by definition, right? The other way is to compute these forces F1 on 2 and F2 on 1, right? That's a little more complicated, but not overly so. Let's stick with the simplest way, which is basically let's just know what the acceleration is. It's just basically we know that if we have acceleration, that must be due to the net force. Okay, so the force net on 1 is equal to the mass of 1 times the acceleration of 1. Well, the acceleration of 1 is basically the same as everyone's. Everyone's accelerating 0.1 meters per second squared. Right? So this is going to be equal to the mass of 1, which is 10,000, times the acceleration, which is 0.1 meters per second squared, which is basically 1,000 newtons. Right? That's very simple. Okay? Now D, we can just do the same thing in this case. Basically, again, what's the net force acting on the train car? Well, the net force acting on a train car is equal to the mass of the train car times the acceleration of the train car. The acceleration again is the same as before, so this is going to just be 20,000 times 0.1, which is acceleration meters per second, is equal to 20,000 newtons. Okay,